More to this topic. My name is Dr. Manoranjan Oja, Assistant Professor, Department of Basic Science, Chemistry, SR University. This topic today we'll discuss, that is ferro electricity, ferro antiferro electricity, piezoelectricity, and pyroelectricity. So we'll discuss what is this meaning, and also we'll discuss what are the materials is shown this kind of a property. So what is ferroelectricity? So ferroelectricity is a property of a certain dielectric material that exhibits spontaneous electric polarizations even in the absence of an external electric field. What is meaning is that, so let's say we have a materials we placed in the external magnetic field, then this dipole of this compound will orient in particular directions to get the uh, polarizations. But in the absence, we are not providing any electric field in this material. But even though inside of the compound that is having, for example, here different ions is there, that will orient in a particular directions, then it will show the polarizations of the molecules or the compound. When without the presence of the electric field, if the compounds having the dipole moment or polarization it is having, that is in internally, then we call it the ferroelectricity. It's kind of a same as that of ferromagnetic compound, where the magnetic moment it is having the compound in the absence of electric field. We can observe similar way here, that the dipolar or polarization is taking places inside the molecule without the presence of electrical field. So that is called ferroelectricity. And the polarization directions of the polarizations can be reversed by the external electric field. For example, if you see here, that is, let's say this direction will be one polarization dipole, and another directions it is having these directions. In overall, if you see, the molecules is having the dipole or polarization, so dipole moment. So when you will, let's say in overall the dipole moment in these directions, then when we will apply the external field, these directions can be changed to here, these directions or direction like this. So means these directions can be reversed by applying the external electric field, that is in the compound of ferroelectricity. How that ferroelectricity origin, what is the reason how it is happening? That's let's say inside the compound there are different kind of ions, the one positive and negative ions. When these positive ions and negative ion in there is not in the same place, that have it different places, then there will be dipole moment. For example, for this one is these directions. When this dipole moment is not cancelling each other, it is having total dipole moment in the compound, then we can get the ferroelectricity. So non-centrocentric crystal structure, for any crystal structures, if it's centrosymmetric, then the dipole moment whatever is having in the compound, that will be cancelled by each other. So then we cannot get this permanent dipole moment or the resultant dipole moment. So that's what non-centrosymmetric compound is observed for this ferroelectricity. And unit cell with permanent dipole moment, that is means in unit cell whatever the ions is occupying in that, then overall there should be one dipole moment, then only we can get the ferroelectricity. So otherwise we can't get. For example, this one, if you see in the different orientations for the permanent dipole moment there, so we will get the for ferroelectric properties of the materials. Now something is called the domain. Means in the compound some region where the arrangement of the dipole in a particular directions. From there we can assign or you can tell that this is carrying the property behavior of the molecule. Then we call it as the domain of the properties of the molecule. That is for in this case it is ferroelectric domain, means the sections of the particular portions of the molecule which is carrying the properties of the materials, that is called domain of the materials. property domain. So polarization reversal means that when, let's say, for this compound overall in unit cell, this polarization is in these directions, but when we apply the electric field, then polarization is in these directions. That as this direction is revised, so we call this polarization reversals. And this polarization reversals can be observed by plotting. This is called hysteresis. So when external field is applied, then domain reoriented themselves. The small sections of the molecules where they're carrying the properties of the molecules. That on reversing the electric field, the polarization does not follow the same path, resulting in a hysteresis loop. So here, if you see in the picture, this is electric field we are applying, and the polarization is taking place in these directions. Now, let's say when we'll apply the electric field, if the polarization is exactly changing in the similar way, then what will happen? This is plot, let's say this is in forward directions, and then we can get the reverse directions like exactly same way. So then means we can tell that forward directions and the backward direction is same, because that plot we are getting here exactly same way. But practically it does not happen that way. So let's say this is our forward directions, then backward directions is following some other path. Or like this, it is forward directions, then backward direction is this one. So as it is not following in the exactly same directions as the forward and backward, so we call is the hysteresis properties or hysteresis loop. So this hysteresis loop is created. So these two important parameters here we'll discuss, that is remanent polarizations, where the polarizations remaining when equals to zero, means the like is ferro electric compound, that compounds having a permanent dipole moment and polarizations. So that's why in the absence of the electric field, polarization will be there. So this is called remanent polarizations. And another is that you need electric field to reduce the polarization, means you can change the polarizations of the materials to zero by using the field. It is called coherent field, that is called EC. Then another thing we'll discuss here, that is called the Curie temperatures. So that the above a certain temperatures called the Curie temperature, the ferroelectric materials lose their spontaneous polarization and become paraelectric. So what does it mean? It is a similar kind of the Curie temperature for the ferromagnetic compounds. So in ferromagnetic compound, what we observe that after a certain temperature, the orientation of the magnet, small magnet in the compound, will be in one particular directions to get the magnetic properties. But if you increase the temperature, then the directions of the magnetic moment is changed, and then it is randomly oriented. Then we will get the compound loses the magnetic property. In a similar way, for this compound, that if we are increasing, we are heating a compound, then after certain limit, that after certain limit, that this dipole moment for a unit cell, the dipole of this resultant dipole moment of a unit cell, they will orient in randomly in different directions. Then it will lose its permanent dipole moment and it will lose its ferromagnetic properties. So that which temperature it is losing, that temperature is called Curie temperatures. Means above the Curie temperature, the compound will not show the ferroelectric properties, and below the temperature it will show the ferroelectric properties. So that particular temperature we call the Curie temperatures. So for example, for barium titanate, for this compound, the Curie temperature is close to 120 degrees centigrade. It means below the 120 centigrade, this barium titanium oxide or titanate, it will behave as a ferroelectric compound. But when it will go above the 120 temperature, then it no longer act as a ferro electric properties. So this is called the Curie temperatures. So this can be useful or can be seen for different compound. This temperature will be different. And above the Curie temperature, these properties of the ferrotinase change to paraelectric, means that permanent dipole moment or polarizations in the compound will be lost or it will become the paraelectric. So what are the applications for this one? This is applied for the non-volatile for electric memory, ferroelectric memory. This purpose or chips purpose when you using this compound has been used. For capacitor also, this molecule has been this type of the compound is also used. For piezoelectric sensors and actuators, we will discuss the what is the piezoelectric properties in the next slides, maybe couple of slides. The electro-optic device, so different kind of electro-optic devices, this kind of compound has been used. For example, just now we have discussed that barium titanium oxides and Ronan salts or lead zirconate titanate. These are the materials which shows the this behavior of ferroelectric properties. So antiferroelectricity means antiferroelectric compound. What is this antiferroelectricity compound is, so in a unit cell, there when previously we discussed that ferro in a electric compound or electricity properties having a compound which have a permanent polarization in unit cell. But in antiferroelectricity compound, there is not a resultant dipole moment or polarization is not there in that antiferroelectricity. For example, you consider this a unit cell. So this is direction, let's say this way. Then next to it, its direction is opposite way. So these directions and these directions is cancelled each other. Then overall we are getting the zero. So there is a dipole moment differences, but overall in the unit cell there is no polarizations. So total polarizations is zero. When it is observed in a compound, we call it is having antiferroelectricity. In difference with the ferroelectricity compound, where the resultant polarization will be there in unit cell, but in the antiferroelectricity compounds, there will not be any resultant polarizations in the unit cells. So means the dipole whatever is having in one section is cancelled by the next section. For this one, let's say this direction exactly similar, next one is opposite directions, so it is cancelling each other. So that's why we are getting that antiferroelectricity. So dipole moment arrangement, we will see that here that dipoles in neighboring unit cells are oriented in opposite directions. So overall we are getting here 0. This arrangement cancel out the overall polarizations. The structure is ordered but produces no spontaneous polarizations. So because every unit having a one polarizations, but next one it is in opposite direction, so it is cancelling out totally. So that's how that dipole arrangement is there, and because of this arrangement we are not getting a resultant spontaneous polarization. So spontaneous polarization is 0 in the systems. The phase transition on application of strong magnet, when we will apply the strong external electric field, then what happens that anti-ferroelectric materials can transfer into the ferroelectric compounds. What is happening that when we will apply the electric field for this strong electric field for this compound, then the orientations of the dipole for unit cell, it may change. If it is changing, then it may not be in the perfectly opposite to each other. So that's why resultant the dipole moment we can get or polarizations we can get. So some kind of a will induce the spontaneous polarizations in the compound. So in the applications of the electric field, so when antiferroelectric substance is there, so we can use the electric field to change its property from the antiferroelectricity to ferroelectricity. These transitions can be takes place by applications of the strong magnetic field. So we need very strong magnetic field for this process, and it can be transferred from the anti-electric properties to the materials to ferroelectric properties. And temperature also can induce the phase transitions. This can be also done by from antiferromagnetic to para-electric. Means this in the antiferromagnetic there is a dipole moment or permanent dipole unit cell, but it is cancelling each other. But when we heat it, then it may also can be converted to antiferroelectricity to paraelectric. So where the resulted or this in one unit we had a dipole that can be also nullified by increasing the heating maybe. So this process when you are doing it, then we can get from the electric properties to the paraelectric properties of the materials. Dielectric behavior. So how the dielectric behavior is happening? It shows the double hysteresis loops in the polarization versus the electric field. Dielectric constant shows anonymous near the transition temperatures. So here you can see that what is called is the hysteresis loop, double hysteresis loop. So let's say for this one, this is our electric field, and this respectively polarization is taking place. So we are applying here electric field, then polarization is taking places. Now, when we are increasing the electric field, if you see, then sometimes it is going, see electric field is applied this much, but there is no polarizations. Polarization is zero. Now again we increase the electric field, then polarization suddenly is increasing and changing. In again when we are decreasing, so then that polarization is decreased. But if you see here, so electric field is decreasing here, but there is no change in polarization, and suddenly after crossing this point, then polarization is changing. So at instantly the polarization is not changing with the increasing the electric field. So there is some kind of lagging is takes place between the polarizations when electric field we applied. So we discussed earlier that different kind of a temperature is there to antiferromagnetic to convert to the paraelectric compound or paraelectric to ferroelectric compound. The temperature previously we discussed, one is called Curie temperatures. So here different kind of a example if you see here, that is called lead zirconate oxide, zirconium oxides. This shows an antiferromagnetic properties of the perovskite structures. It shows the antiferromagnetic properties. Whereas the for silver niobate, for here this compound also shows the antiferroelectric properties. So it has been used for the high energy storage capacitor or electromechanical device or switching device or different kind of switching device also it can be used. Piezoelectricity. Piezoelectricity is a compound, is a one type of compound. So what it's happened that in this compound when you press it, you are applying some pressures. So you are squeezing in that compound, then it will produce that electric charges. So electrical changes will happen in the molecule due to the mechanical stress. Mechanical stress means from outside we are stretching it or compressing it. Then conversely, when it will when you are removing this stress, or again we are removing the compress, then it mechanical deformations will happen. Then electric field is applied. So this two way means what we are doing here, that we are producing the electric charge when this materials is mechanically stressed, and conversely it undergo mechanical deformations when electric field is applied. So reverse way. So what we are doing, we are pressing it, then electrical charge is created in the produce, and in the similar way by using the electric field also we can change and we can make the mechanical deformation of the compound. This when we get this kind of a properties we call it a piezoelectricity. Cause of the piezoelectricity is that it occurs in the crystal that lack of center of asymmetry. And mechanical stress causes the displacement of ions within the crystal lattice. This displacement creates a electric dipole moment. Means previously there was no permanent dipole moment of the compound, but when you are pressing it, then orientations of the ions will be changed, or positions of the ions will be shifted. Then due to the positions of the ion is shifted, then we will create the dipole moment in the molecules. As dipole moment will be created, then it will change, or it will show the electric charges in the molecule. So we will get a polar, I mean, this compound become the polarizations. Opposite way, when electric field will be given or in this compound, then it will happen some mechanical stress or mechanical deformations, it will happen in the compound. So that's how it is changes. So this is this kind of behavior when it shows the compound. This is called piezoelectricity. So it means electricity or electric charge is generated in the molecules by the applications of the mechanical stress, or that is for compressions, or by removing the compressions. So by the mechanical stress, we are getting the electricity in the compound. This is called piezoelectricity. So here some kind of a in pictures shown, that is called direct piezoelectric effect. So what we are doing, we are making the mechanical stress, means let's say we are compressing it, then electric charge we are getting. So this is called a direct piezoelectric effect. But here what you're doing, opposite, just opposite, that we are giving the electric field, then mechanical strength is happening. This is called inverse piezoelectric effect. So how we can calculate this one? By using this equation. P means polarization we are calculating due to the piezoelectric means mechanical strength. That is polarization P equals to the what is the piezoelectric coefficient, the D, and the applied stress. So how much stress we are applying multiplied with the piezoelectric coefficient. So then we can get the total the polarizations of the compound. So these properties is observed in the quartz or lead zirconate titanate. This has been used, or also in applications for quartz oscillators or watches or clocks or microphones and the speakers. Also this kind of a compound has been used. Pyroelectricity. Pyroelectricity is a one kind of electricity property that materials to generate the temporary electric polarizations when there is a temperature change. Means inside of the compound we are heating it, then there will be inside the compound there will be change in temperatures. Due to the temperature gradient, then electric dipole moment will be created. Polarizations will take place in the compound. That is called the pyroelectricity. So means we are exposing the compound in the temperature and thermally. Then due to the thermal regions, there will be a shift in the charges. So it will create the dipole moment, and because of the dipole moment creations will have the polarization in the compound. That is called pyroelectricity. Pyroelectricity crystal possesses permanent spontaneous polarizations. When temperature changes, the magnitude of polarization is also changed. This results in a flow of surface changes. These effects occurs only during temperature variations, not constant temperatures. So means we are changing the temperature. Due to the changing the temperature, we will see the electric behavior of the compound, that is called pyroelectricity. So these are the compound has been used for the which shows the pyroelectricity. This is the we can calculate the equation, that is called pyroelectric coefficient P equals to dP by dt, means how the polarization is changing due to the temperature change. So this ratio which give the pyroelectricity. So if we want to calculate the pyroelectricity coefficient, so means how the polarization is changing, how much it is changing the polarization, or with unit change of the temperature. So relationship with others. So we will see here some kind of relations in this category of the electricity compound, that is ferro, antiferro, pyro, and piezo compound. All pyroelectric substances are piezoelectric. So if you observe any pyroelectric materials which is shows the which shows the polarizations properties due to the changing in heat or temperature, this also shows the piezoelectric behavior. And all piezoelectric materials are dielectric. So means all the which are we are pressing these materials this compound shows the electrical behavior of polarizations, permanent polarizations takes place in the molecule, that is called piezo by the applications of the mechanical strength, that is called piezoelectric materials, that are all dielectric in nature. But all dielectric nature are not piezoelectric or pyroelectric. So all pyroelectric compounds are piezoelectric, and all piezoelectric compounds are dielectric in substance, but opposite way, all dielectric substances are not the piezoelectric or the pyroelectric. So what is the comparisons? Here the comparison is there for this four type of the compound properties, that is ferroelectric properties, antiferroelectric, piezoelectric, and pyroelectric. So spontaneous polarization is there in ferroelectric, yes, because in unit cell you have a particular orientations of the dipole is there, so we will get the spontaneous polarizations. So we do not need any external electric field to see the polarizations. So in for ferroelectric compound we have a spontaneous polarizations. Antiferromagnetic, yes, it is also having the spontaneous polarizations in unit cell, but it is cancelling with the next neighbor polarizations. So one unit it is having in which directions, and the next unit is having in opposite directions. So spontaneous polarization is there, but it is cancelling out one by one. So that's why resultant we get the zero. That is called antiferroelectric compounds. Now piezoelectric compounds, no, that is there is nothing spontaneous polarizations, only because of mechanical strength when we will apply, that time only this polarization is takes place. So there is no spontaneous polarizations in the piezoelectric compound. And pyroelectric compound, yes, polarization is there. So due to the heating, we are getting there is a spontaneous polarizations is observed in the pyroelectric compound. So net polarizations for ferroelectric compound, yes, because spontaneous polarization is there and it is not cancelling each other by the neighbors polarizations. So we will get the non-zero. Net polarization is non-zero. But anti-ferromagnetic, at it is cancelling each other, so that's why you will get the zero. And piezoelectric, because of the mechanical strength it is induced. Previously it was nothing, no polarizations, but it is induced due to the uh, mechanical strength. So this is called induced net polarization will be there. And pyroelectric due to the heating only. So when temperature dependent is there, means heating is there, or in different temperature, when we are changing the temperature, then only polarization is taking place in the molecule. So pyroelectric is totally temperature dependent. Field reversibility. So field reversal means we are applying the electric field, then it can be reversed the directions. Yes, for ferroelectric substance, there these directions of the polarizations can be reversed by applying the electric field. But for the antiferromagnetic, we need very strong electric field to change it, because all are in neighbor as opposite to each other. And for electric piezoelectric substance also, we can change the orientations of the or the polarizations directions can be changed by using the electric field. But pyroelectric is only the temperature dependent, so it cannot be changed by using the field reversibility. Temperature dependent, yes, ferroelectric also strong temperature dependent, because with increasing temperature the orientations of the dipole can be changed, so polarizations can be changed. For ferroelectric, antiferroelectric, for this substance, this can be changed very rapidly or very strongly, it can be changed. But in case of piezoelectricity, but we are making it by pressing it, so not that much can be changed by the temperature. For pyroelectric is the essential. Pyroelectric means we are only getting the polarization due to the temperature gradient or temperature change. So that's why it is very essential for the pyroelectric substance. So what we have discussed in this sections is that what are the properties or what is the meaning of the ferro, antiferro, piezo and pyroelectricity properties for the materials, and how it happens, what is the mechanism for it. We have discussed that part as well. Also we have discussed that who is the applications of this phenomena, where we can use it, the sensor, memory elements, actuators, and detectors, and understanding their principle also we have observed here. We understand how the this process is taking places. Okay, we'll conclude in the session here.